Okay, hello everyone. Welcome back to this tutorial video series on theoretical computer science. In this video, we'll be discussing the very first computational machine that we'll be seeing in this course and in this topic, which is known as the deterministic finite automata. So we'll get into what exactly that is in just a few seconds. So essentially in this section, we'll be discussing what a Dfa is, how to navigate through one, how to compute with one, building an example Dfa from scratch. And then we'll also tie this in with the very related topic or concept of regular languages. So regular languages, regular languages are essentially just a very specific type of language that are related to DFAs through a certain property, okay? But before we get to that, we need to introduce what Dfas are. And so that's what we're going to start with. So, before I give you the more formal definition of DFA, I wanted to give a more high-level kind of intuition or introduction to it. So, a DFA is really a computational model, okay? So it's a simplified model of what we know as a computer. So a DFA takes some input. So to illustrate what a DFA is, I'm just going to illustrate it with a box for now, some abstract box. So I have some abstract box, which is going to be my DFA. Within this box is going to be the main processing unit, right? So the main brains of the computation are in the processing unit. So, or they're in what we also call the control unit. So let's say we have this control unit, okay? Just think of this mini, very simplified processor. So what this control unit is going to do is it's going to receive an input. And this input is going to have type string. So its input is going to be of type string. So for instance, on the input tape, so you can assume that how I'm giving this input to my machine is through an input tape. So you can think of these very old machines that actually used to read tape to get their input, or you can just think of it as just this kind of place onto which my processor reads stuff. Okay, so just imagine it however you want. You just have to think of it as this place onto which I have my input string. So my input string is divided into a sequence of symbols. And this sequence of symbols forms a string. So imagine I have the string hello, right? So I have the classic hello world string. Well, in this case, I'm just going to have hello. So essentially what happens when I give an input string to my control unit is it's going to start. So imagine I have a certain place in my processor where I start all the computations. So it's going to start there, right? It's going to start there. I'm going to represent the start as a state, okay? Or just a node in a graph. And what it's going to do is it's going to read the very first symbol on my tape, okay? So the very first symbol on my tape, hello, okay? And so here, my input string is hello. And so I'm imagining actually that my alphabet is just, the English alphabet, right? Okay. So there's a related alphabet to my input. So it's a string, but actually it's a specific type of string. And what's going to happen is my control unit is going to start at this state, right? So I just want to highlight that this is the start state. So the state or node at which every computation begins. And based on the first thing that it reads, so based on the fact that it sees an H, it's going to do a certain computation. So you can think of this certain computation as the control unit going to a certain place, a certain region of its processing where it's going to do something based on what it just saw, right? So perhaps because it's on H, it's going to go from my initial state, which I'm going to denote Q0, to another state, which I might denote, let's say, Qi, right? Okay, and then my pointer is going to move up a symbol, and it's going to go to the E. And then at the E, my control unit is now going to be in a different configuration, because now it's at Qi. And based on this configuration, it's going to read E. Okay? It's going to read E, and then it's going to do something else. So maybe once it reads E, it's going to go to another state. Okay, so maybe if it reads E, it's going to go to another state, Qj. Okay, and essentially a DFA is what I'm describing here. So together, these two things are going to form a deterministic finite automata. There's going to be a bit more details to see why exactly it's deterministic and why it's finite. But this is the general idea, high level, of what this kind of machine could do. So essentially, it can navigate through its processing unit, do computations based on the input string, and once it finishes the input string, so once it gets to the end, the final state in which the control unit lands is going to determine whether the string has been accepted or rejected. And so that's the output. The output of my machine is either an accept or reject. So accept means that your machine returns true upon reading W. And then a reject is as if your machine returned false upon reading W. Okay? So this is what a DFA looks like at a high level. Okay? And so to give this a much more concrete flavor, I'm going to give a more formal definition, which you might see in more theoretical lectures, but I think it's also important to do it in a tutorial style lecture, because it really gives you a concrete sense of what a DFA is and what it's capable of. So a deterministic finite automata, or DFA, M, is this 5-element tuple. So it's a tuple that contains 5 elements. Q, which is the set of states, right? So remember how I was talking about your control unit is a graph of states. So Q is going to be the set of those states. Sigma is the alphabet, so it's the keyboard onto which you can type in strings, right? So in the previous example, it was the English alphabet, but typically it can also be the binary alphabet, okay? Delta is the transition function, and we're actually going to come back to delta because it's the most important part of M. Q0 is the initial state, which is unique. So it's also what we know as the start state, right? So in the previous slide, where I said that I was going to start here, so this is my start state, which is denoted by Q0 in my definition. And finally, F is the set of final states, okay? And so a DFA is a machine that takes as input a string and returns either an accept or a reject. And it's going to accept a string W. So W is accepted if when M processes W, M lands in a final state. Lands in a final state after traversing the graph, which I'm going to come back to in a second because the graph is actually related to delta, the state transition graph based on the walk W. So my string W is actually a sequence of symbols, W1, W2, W3, until Wn. And so this sequence of symbols is actually a walk, right? So it's a walk because from W1 is I'm going to start at Q0, and by reading the label on the appropriate edge, I'm going to go from Q0 to my next state Qi based on the edge W1. So if I'm at Q0 and I have the label W1, so let's say that's A, then this is going to tell me that I'm going to go to Qi. Okay, and this is actually a good way of introducing the transition function delta. So the transition function takes a state Q and a letter sigma and returns another state Q prime. And essentially, delta is what tells the machine what to do as it's reading the input tape. So it's saying that if you're at a state Q, right? So you're at a state Q and your pointer is pointed to sigma, right? You have your input tape, your pointer is pointing to sigma, and you're at state Q. What do you do once you read sigma at Q? Well, you read sigma and you go to Q prime. Whoops. You go to Q prime. Okay? And now, if you combine all these things, you're going to get a deterministic finite automata. So, why is it deterministic and why is it finite? So I don't have this on this slide, but let me add it here. So y Dfa. So automata is just the name that we give to this computational model, right? Why is it deterministic? So why is it deterministic? Okay. So it's deterministic because every single movement or every single process, computation, rather, I should say, every single computation that your DFA makes is set in stone. It can be exactly predicted, okay? So why do I say that? That's because if I'm at, say, Q1, okay, and I read my symbol A, then the only thing that I can do is go to Q2, okay? That's the only possible option. Okay, that's why it's deterministic. It's because you always have a single option. It's finite, okay? It's finite because you have a finite memory, okay? So if we go back to the previous slide here, you'll notice that nowhere in my control unit input tape drawing have I created a external memory. And this is what's very particular of DFAs, is that it does not have any memory. It has a finite set of states, and so it can only remember a finite amount of things. And then finally, there's a very specific relation between DFAs and languages. We say that the language L of M is the set of all strings. It's the language containing all the strings accepted by M. And these strings are the ones that start at Q0 in my machine M and go to my final state in F. Okay? Or so more formally, L of M is all the words in sigma star, such that if I start at Q0 and I read W starting at Q0, going through my state transition diagram, I get to a final state F. Okay, that's how you define the language recognized or accepted by your machine M. So this is the language accepted or recognized okay? And that's how you would define LLM, and that's the relation between DFAs and languages, is that DFAs are language recognizers. So machines, DFAs M, are language recognizers. They recognize, so they essentially take your universal space, your sigma star, and for a particular machine M, they partition it into the set of strings accepted by M. So this is the strings that are accepted by M. And here, the strings that are not accepted by M. Okay? All right, so in the next video, we're actually going to look at a concrete example and then work through the creation of DFA based on a language.